Does time actually have a direction? A lot of people think they already understand time pretty well. Is not it just the space-time that Einstein's theory of relativity talks about? But are you really sure what you think you know is correct? Honestly, most people have no idea what time actually is. Some even use clocks and calendars to keep track of it. But those are just numbers. They are not time itself. It is like thinking you understand heat just because you have a thermometer. In reality, time is much stranger and more profound than we have been told. So next, we are going to spend over 30 minutes breaking down and examining time in detail. We will also take a deep dive into whether we can actually jump to the future or go back to the past. Please pay attention. I am not talking about theory. I am talking about real, practical issues. Time is something we use every single day. But have you ever really stopped to think about what it actually is? It determines our routines, our aging, even the changes in the entire world. It is like a river, quietly but steadily pushing us forward. But here's the question. Is time really what we think it is? Time really what we think it is? Is it just a tool to help us distinguish the past, present, and future? Or does it actually hide the deepest secrets of the universe? On the surface, time seems pretty simple. Clocks tick. Calendars turn page by page. We get up, eat, and sleep in order, living each day smoothly. We flip through the calendar and plan a get-together for next Tuesday. Time just seems like a framework for organizing our lives. The more scientists studied, the more things did not add up. Modern physics tells us time is not something that exists on its own. It is not a clock quietly ticking somewhere. In fact, it is a partner of space. What does that mean? Imagine this. Outer space is like an endless, invisible giant sheet, smoothly spread out in all directions, holding up everything. Stars, planets, galaxies, even light has to travel along it. But this sheet is not just space. It also includes time. So scientists gave it a name. Space-time means time and space are actually one and the same. They are not two separate dimensions, but rather a woven grid. Normally, we think of space as where left, right, up, down, near, and time as when yesterday, tomorrow, morning, night. They sound like completely different things, but science tells us they are not. They are like the horizontal and vertical threads in a piece of fabric. If you pull on any one of them, the whole fabric will change shape. The concept of space-time was only formally proposed in the early 20th century, and once it appeared, it completely overturned the way scientists viewed the universe. You have to understand, before that, space and time had always been seen as two completely separate and absolutely unchanging things. Time was thought to be exactly the same everywhere, always ticking at the same rate. And space is like a grand stage that never moves. Every performance in the universe takes place on it. But this seemingly stable system was soon broken by one person. That person was Einstein. He stepped out and completely overturned this entire way of thinking. In his general theory of relativity, he proposed space and time are not lifeless. They are not just a backdrop. They are things that can move. They can be stretched and compressed, or even bent. They can even ripple in waves. And this kind of deformation is related to matter and energy in the universe. In other words, whoever is heavier can make the surrounding space-time react. More importantly, gravity is not that invisible pulling force we always thought it was. In Einstein's view, gravity is not a force at all. Instead, mass bends space-time. As a result, other things just slide down along that curve. Sounds kind of mind-blowing, right? No worries. We can keep using that rubber sheet analogy from before. Imagine you spread a rubber sheet over a table that is space-time. If you place a bowling ball in the center of the membrane, because it is so heavy, it will create a dent in the membrane. This step represents how massive objects like stars or planets bend space-time. Then, if you place a small ball at the edge of the membrane, the small ball will slowly roll toward the big one. It is not because something is pulling it, nor is it being sucked in by anything. It is simply rolling down the slope of the membrane on its own. This is Einstein's explanation. Gravity is not a pulling force. It is the curved space-time guiding the movement of objects. In other words, massive objects change the shape of space-time. Other objects then move freely within this curved space-time. The reason we feel gravity is actually just because we see the result of objects being guided along their trajectories. And what is even more interesting is that this influence is not one way. It is not just big things pulling small things. Small things are also pushed by space-time in the same way. They slide in along the curved path. This kind of curvature does not just bend space, because time gets dragged in as well. After all, Space and time are bound together. If a star makes a dent in the membrane, it is not just space that is dented. Time itself is. According to Einstein, time is nothing like the evenly flowing, eternally steady metronome we imagine. It is just like space. It can also be stretched, compressed, or even slowed down depending on the surrounding environment. There is not a universal time standard in the entire universe. What is even more unbelievable is, in Einstein's theory of relativity, this thing called time does not actually come labeled as past, present, or future. Those words, to put it simply, it is just a tool we humans use to describe our subjective experiences. Physics itself does not care about this at all. In the equations of general relativity, you simply can't find which is the past and which is the future. It only describes one thing: how time changes, how it gets stretched, compressed, or even twisted together with space. That is all. In Einstein's view, time is just another dimension. There is no fundamental difference between it and the 3 dimensions of space. You could say something is 5 meters north, 3 meters south, and 10 meters east, but you also have to add one more thing. At what time does it appear? So in 4-dimensional spacetime, you need 4 coordinates to truly describe an event in the universe. 3 spatial dimensions, plus 1 time dimension, together determine where and when something is. But here's the problem. In space, we can go anywhere we want, left or right, forward, backward, up, or down. But what about time? We can only ever move in one direction forward. It is as if we are being pushed by some force from one moment to the next. In the mathematical world of general relativity, time does not move. All points in time are already there from the start. Like dots on a canvas, this theory does not tell you which moment is now, nor does it say any moment is more special than another. It simply lays out the entire structure of space and time in the universe, including all the past, present, and future, and presents it to you all at once. An extremely counterintuitive idea emerged. Maybe time is not actually flowing at all. Maybe it simply exists quietly. Just as every location in space exists simultaneously, every moment in time might also already be fixed in place. We are just experiencing them one after another in a certain order. But from the perspective of the universe, they have all long been woven into this get-up of space and time. Einstein himself once said, "The distinction between past, present, and future is only a stubborn illusion." He was not saying that time is fake, but rather, what we think of as the flow or passage of time might just be an illusion created by our brains. It is not a law of nature itself. Here's the problem. If that is really the case, then why can we only remember the past but never the future? Why does not a broken cup just jump back together on its own? Why do we always feel like time is moving forward? The equations of physics do not actually favor any particular moment in time. It does not say now is the most important, nor does it say the past is already over. So where does our sense of direction actually come from? This is the famous arrow of time problem. In Einstein's equations, time is just an ordinary coordinate, essentially no different from left or right. But our everyday experience tells us very clearly. Time has a direction. It moves from the past to the future, always forward, never looking back. We are born, we grow up, we age, and finally we die. When we light a match, it burns to ash. It can never grow back the other way. In the real world, there is always this undeniable sense of one-way direction, and to figure out where this sense of direction actually comes from, scientists do not look to gravity, nor do they rely on relativity. Instead, they turn to thermodynamics, a discipline that studies heat and the flow of energy, especially one of its core laws. The second law of thermodynamics puts it plainly: in a closed system, entropy, the system's degree of disorder, will only increase. Simply put, everything goes from order to disorder. Order turns into increasing chaos. For example, if you drop an egg on the floor, the shell breaks and the yolk spills everywhere. That is an increase in entropy. The level of disorder has gone up, but if you wait for it to reverse itself, for the fragments and sticky yolk to somehow reassemble into a whole egg, in theory, it is not absolutely impossible. But the odds are so small they can be ignored. It is almost impossible for it to happen spontaneously, and it is this one-way evolution from order to chaos that gives time in our world sense of direction. This is the origin of the arrow of time, and it is not just about eggs. It is connected to everything in the universe, from stars burning out, to ice melting, to the ongoing expansion of the universe itself. Every process, Every system is sliding toward a state of increasing disorder. The increase in entropy creates what we perceive as before and after. It gives time its arrow. Even though, in the fundamental laws of physics, there is no place for this arrow at all. You can think of it this way. It is like reading a book. Page 10 and page 50 both exist at the same time in the book. They are all printed on paper, but we can only read them page by page, from beginning to end. In the same way, this book of space-time that is the universe, all moments might already exist. It is just that because of our existence, we can only read it in one direction. What is interesting is, if you play a video of an egg being smashed in reverse, you immediately sense that something's off. It is not just because it looks unnatural. It is because this reversed footage violates a deeper underlying rule. That is exactly why we can instantly tell whether a video is playing forward or backward. We can see it right away. It is because we can subconsciously recognize the arrow of time. But things get even stranger at this point. The fundamental laws of physics have never actually forbidden an egg from putting itself back together. They just tell you that the probability of such a reverse process is so small it is almost zero. It is not completely impossible. From the perspective of the equations, time can move forward or backward. The math makes perfect sense. What does that mean? It means the one-way direction of time is not hardwired into the equations of the universe. It is more like a phenomenon we observe. It is created by the way things are arranged, by the path things take as they unfold. It is a feeling that is manufactured. It is why we feel like time is a one-way street that only moves forward. But when you look at the fundamental rules of physics in the universe, this sense of direction is not embedded in any fundamental law. In other words, now is not all that special. The future is not really that out of reach either, and even the past might not be as distant as we think. But if all of this holds true, then a bigger question emerges. If time can be bent, and something gives it direction, then what about us? Is it possible to travel against the arrow of time and move through it? To answer this question more deeply, let us talk about a true story. Do you remember that astronaut who was in space when his own country ceased to exist? That was Sergei Krikalev. To be honest, he was the most legendary space traveler of his era. For nearly 20 years, Krikalev carried out a total of 6 space missions, spending a total of 803 days, 9 hours, and 39 minutes in space. In other words, he spent more than 2 full years, orbiting several hundred kilometers above the Earth. Inside the space station, every day, he looked out the window, watching sunrises and sunsets flash by at an astonishing speed. The pace of time is so fast, it is hard for people on the ground to even imagine. His career as an astronaut truly spanned an entire era. Starting from the Cold War period, in 1988, he took his first flight on the Soviet Soyuz Team 7 spacecraft, arriving at the Mir space station that was the symbol of glory for the Soviet space program. Later, he returned to the Mir space station multiple times. He lived and worked in a microgravity environment, sometimes staying for months at a time. Supplies were limited and conditions were tough, but he never complained. Became well known for being calm, highly skilled, and able to spend long periods away from home. But in 1991, he was still on a mission in space. When the Soviet Union on Earth suddenly collapsed, he instantly became a citizen of a country that no longer existed. Is not that awkward? However, with the end of the Cold War, space exploration shifted from hostility to cooperation. Krikalev also became a witness to history, began flying on the space shuttle with NASA astronauts, and took part in the collaborative construction of the International Space Station. He became one of the key figures in this program. In 2000, he participated in the first long-duration mission on the International Space Station. 5 years later, he went to space for the 6th time. This trip brought his total time in space to over 800 days, setting a new record at the time. During these missions, Krikalev experienced a daily life in space that only a handful of humans ever have, floating while eating, sleeping in zero gravity, and repairing equipment in weightlessness, even celebrating holidays in orbit. He was not just a tourist coming back in a few days. He was truly a representative of humanity living in orbit. But more importantly, he was not just a space traveler. He really is a true time traveler, because he actually went to the future. You heard that right. That is exactly it. Why do we say Krikalev is a time traveler? Because when he was flying in orbit on the space station, his speed was astonishing. 7.66 kilometers per second. That works out to about 27,600 kilometers per hour. That is not just cruising, he was flying around the Earth, according to one principle of Einstein's special theory of relativity. It is very clear, the faster you move, the slower time passes for you. This is called time dilation. Krikalev was flying in orbit. His body And the clocks around him actually ran just a little bit slower than time on Earth. For example, 1 second passes on Earth, but for him, it might only be 0.0 seconds. The difference is extremely tiny, but it does exist. You might think this difference is too small to matter. Do not forget he spent a total of 803 days in space. Add up all those tiny differences, and it comes to about 20 milliseconds. In other words, he is actually younger than us on Earth by 20 milliseconds. Does not it sound like a joke? But this is not science fiction, it is a real, measurable physical phenomenon. This difference in youth means he actually made a small jump in time. When he returned to Earth from space, now was just a little bit ahead of ours. He has lived just a little bit more of the future than those who never left Earth. To put it simply, it is not that he walked into the future faster, but rather that, while he was not paying attention, we passed through time even faster. This is not made up. 1971. American physicists Haffill and Keating conducted an incredible experiment. They took 4 highly precise atomic clocks, put them on commercial airplanes, and flew them around the Earth. Then they compared them with identical clocks on the ground, and the results were actually different. The clock on the plane runs slower. Exactly as Einstein's theory predicts, time dilation really exists. This effect has its own specific equation. It is called the time dilation formula. Comes from special relativity. You do not need to look at the formula. Just remember one key point. The faster you fly, time passes more slowly for you. We do not notice it in our daily lives, because our speed is like that of ants crawling, compared to the speed of light. But it is different in space. A spaceship orbits the Earth at over 28,000 kilometers per hour. It is fast enough that even a few milliseconds make a difference. It can still be detected. But what if you could fly close to the speed of light? Then time dilation would not just be on the scale of milliseconds. It would be on the scale of generations. Imagine this. You board a spaceship and travel at 99.9% the speed of light for 1 year. Then you return to Earth, only to find that decades have passed here. The people around you may have grown old or even passed away. But for you, it only felt like a year. Your present is no longer aligned with their present. You can think of it like this. Others are watching a movie at normal speed, while you are watching it in slow motion. As time goes by, you and them will fall further and further out of sync with the plot. The movie is already over for them, but you are only halfway through. That is what it feels like to approach the speed of light. Your time slows down, while the universe's time speeds up. Do not think that only speed can change time. Gravity can play some big tricks too. In general relativity, Einstein told us that gravity is not actually a pulling force. It is actually caused by massive objects, warping the structure of space-time around them. This distortion affects not only the direction of space, but also time itself. The closer you are to a massive object, like a star or a planet, slower time passes for you. This is called gravitational time dilation. It is also the wildest and most counterintuitive part of Einstein's theory. There is a scene in the movie Interstellar that left countless viewers stunned. The astronauts aboard the Endurance spacecraft fly toward a supermassive black hole called Gargantua. They land on a planet extremely close to the black hole, and it is this very choice that almost made them say goodbye to their own era, because the black hole's gravity is just too strong. It warps the surrounding space-time. Not just a little bit, it is exaggerated to an unbelievable degree. Time on this planet moves 70,000 times slower than on Earth. An hour there equals 7 years on Earth. They spend just a few hours on the surface, carrying out their mission, but when they return to the ship in orbit, they realize the teammate who stayed behind to guard the ship has already aged over 20 years. This scene looks like the ultimate in science fiction, but you should know, this is not just some random plot made up by director Nolan. This concept was actually designed with the involvement of Nobel Prize-winning physicist Kip Thorne. He served as the scientific advisor for Interstellar. Using Einstein's general theory of relativity, he ensured the film's depiction of black holes and time dilation was accurate. These are all real and feasible physical phenomena, and this is not just a special effect that only appears near black holes. Even in everyday life, gravitational time dilation can actually be measured. In the 1970s, scientists conducted an experiment, took 2 ultra-high precision atomic clocks. One was placed at sea level, and the other was placed on a mountain 2,300 meters high. What was the result? After comparing them 11 days later, the clock on the mountaintop really did run just a little bit faster. Why is that? Because the mountaintop is farther from the center of the Earth. It experiences less gravity. Space-time is less curved there, so time passes a little faster, but the clock at sea level is closer to the area with greater mass on Earth, so time moves a bit slower there. How small is this difference? Only a few hundred millionths of a second, but the instruments at the time were already precise enough to measure it clearly. So you see, Whether you are flying fast, staying close to a gravity source can change the speed at which time passes. But if we want to talk about real-time travel to the future, we have to look at a third method, the most sci-fi and the craziest one, warping space itself. In 1994, physicist Miguel Alcubierre, he proposed an idea that left everyone stunned. The Alcubierre drive, he said. Instead of making a spaceship go faster and faster through the universe, why not do the opposite? Make space itself move. His idea was this. If you could use the mathematics of general relativity to squeeze space-time into a special structure, take space and squeeze it into a special structure to create a bubble. Inside this bubble, time feels normal to you, but the bubble itself moves faster than light relative to the outside universe. Simply put, the spaceship itself does not need to travel faster than light. Instead, you sit inside the bubble and let space carry you along. The result is, to an outsider, flash by in an instant, crossing thousands of light years. But to you, it just feels like a short journey, like driving from the city to the suburbs. Sounds crazy, does not it? But mathematically, you really can calculate it. Usually, when we talk about travel, we picture a car driving down a highway, going from the starting point to the destination, relying on speed, fuel, and a complete route. But in Einstein's general theory of relativity, space and time are not just backgrounds. They are like a giant elastic sheet that can stretch, bend, and even ripple. If you could control the shape of this sheet, you would not need to travel through space at all. You could just ride on a moving piece of space. That is how bold Alcubierre's idea was. He proposed, wrap the spaceship in a special space-time bubble. This bubble compresses space in front and stretches space behind, and the spaceship just stays obediently right in the center of the bubble. Not moving at all, but the bubble itself is moving. It is like a wave carrying the spaceship as it glides across the surface of the cosmic ocean. That is why the spaceship itself does not move, yet it can arrive faster than light, and it does not violate any physical laws at all. You can think of it as surfing on a cosmic scale. The Alcubierre drive, it is like grabbing this fabric of space-time and shaping it however you want. You sit right in the middle. Let the entire fabric of the universe roll you along. The point is not just going fast. What is even more mind-blowing is, it can let you jump into the future. Because inside this bubble, the flow of time is completely different from the outside world. While you are inside, you might only experience a few months or years, but outside, hundreds or even thousands of years could have passed. Imagine this. In the year 2100, you leave Earth and fly to some distant planet. To you, it feels like you have only been flying for a year, but when you look back, Earth's calendar has already turned to the year 3100. You have suddenly jumped a whole 1,000 years. But you have only aged 1 year, and what is even more amazing is that inside the bubble, you do not even feel the acceleration, because you are not moving. The entire space is carrying you along. So there is no feeling of being pushed back, no bone-crushing G-forces. You do not need some indestructible shield to block interstellar dust. It is like you are sitting on a lake, floating perfectly still, and the entire universe is racing past you at a mad speed. But here's the problem. How do you build this bubble? Actually, you need a very special material called negative energy, or exotic matter. This substance does not attract things, but repels everything, can make space expand and distort. Sounds like magic. Actually, there is a hint of it in quantum field theory. For example, the Casimir effect. Between two extremely close metal plates, you can detect traces of a tiny negative energy field. The problem is, it is far from enough. Create a space-time bubble. You need a massive amount of negative energy. According to early models, it might require the equivalent of an entire Jupiter's mass. Only then would it be enough. Obviously, that is impossible to build, but there is still hope. A lab under NASA, Eagle Works, seriously studied this issue. Researcher Dreher, her old Sunny White, recalculated it and proposed an improved model. He said, if you optimize the geometry of space-time, maybe you would only need as much negative energy as a car, but that is still far from achievable. But it is way more reliable than Jupiter, at least for now. We can still discuss this issue. We are not just closing the window right away, of course. The problems are still enormous. If you really want to build that bubble, you would have to perform surgery on space-time, and that is something we have absolutely no idea how to do right now. And even if you somehow manage to create the bubble, a new problem would immediately arise. How do we make sure it does not collapse? How do we prevent it from emitting deadly radiation? Any one of these could be fatal. In theory, that warped bubble could keep accumulating quantum radiation during flight. If the bubble collapses at any point, the energy released could not only destroy the ship, but also even the surrounding regions of the universe, could be wiped out. But even with all these huge problems, the Alcubierre drive is still exciting, because it does not break any physical laws. It fits perfectly within the framework of general relativity. It is just that our technology is still incredibly far from it. However, if you are really obsessed with jumping into the future, there is an even crazier idea we can talk about. It is called white holes. We all know about black holes, right? They are the ultimate devourers of the universe. They can suck in anything, not even light can escape. What about white holes? It is actually the opposite. It is a jet engine in the universe. Instead of absorbing matter, it ejects matter and energy outward. You can think of it this way. A black hole is a monster that swallows you whole. A white hole is another kind of monster that only spits things out. Sounds like a wild idea, but actually, this concept comes directly from Einstein's general theory of relativity. When scientists were solving Einstein's equations, they were surprised to find that, besides black holes, there might also exist a kind of mathematical inverse. A black hole is something you fall into and can never escape from. But what about a white hole? You can't get into it at all, because it is always spewing things out. So what does this have to do with time travel? The key lies here. Some scientists speculate that black holes and white holes might be connected by some kind of space-time tunnel, which we know as a wormhole. Suppose you actually found a way to survive passing through a black hole, then you might end up being spit out from a white hole on the other side. And the extreme gravity of the black hole, it will let you travel through time and space, but not across space, rather across time. For example, if you enter a black hole in 2025, pass through a wormhole, and come out from the white hole on the other side, it might already be the year 4025 for you. This journey might only take a few hours, but on Earth, a whole 1,000 years would have passed. You are still alive, but Earth has already moved on to a new civilization. From this perspective, a white hole is like a one-way time accelerator. It won't take you back, but it will throw you into some moment in the future. The problem is that white holes are still just hypothetical concepts on paper, but we have actually observed black holes. We have even managed to photograph one, for example. The supermassive black hole at the center of the M87 galaxy. A supermassive black hole took an entire Earth-sized array of telescopes to capture that iconic orange donut image. But what about white holes? Currently, there is not a shred of direct observational evidence. Some scientists speculate that maybe in the early universe, or under certain extreme conditions, wormholes may have appeared briefly. Some people think they are just freaks that popped out of mathematical equations, and nature never actually produced such things. There are even bolder speculations. Some say those incredibly mysterious gamma-ray bursts in the universe might actually be white holes erupting with energy, but in the end, it is all just speculation. There is no solid evidence yet. Still, the idea is fascinating, is not it? If white holes really do exist, if we could get close to one without being torn apart, maybe we could actually use it, launch ourselves into the distant future. It is like discovering a secret passage left by the universe for the brave, a shortcut that can cross through time. But if all these methods seem too far-fetched, there is still an option that sounds much more down to earth. Freeze yourself and wait for the future to come find you. This is not science fiction, nor is it some high-tech magic that manipulates space and time. Its core principle is just one word. Wait yourself on pause. Then you wait for decades, even centuries, until the future becomes worth waking up for. This is what is known as cryonics. It is not time travel, but more like pausing time. The procedure sounds like the start of a sci-fi novel. As soon as a person is declared dead, note that is death as defined by law, the cryonics company steps in immediately, using liquid nitrogen to rapidly cool the body to -196 degrees Celsius. Goal is to maximize the preservation of brain cells and organ structures to prevent decay or irreversible damage, and then they put you into a metal canister and store you in a specially designed liquid nitrogen facility. You just stay frozen like that, waiting for the future. When they can wake you up, you might not know this, but people have been doing this for a long time. In 1967, psychology professor named James Bedford became the first cryonically frozen human in history. To this day, he still lies quietly in a cryonic chamber, waiting for the miracle of future technology. Since then, many others have followed suit. Some chose to freeze only their heads, betting that the future can rebuild their bodies. Others opted for whole body preservation. Just think of it as putting a whole person into storage. Ning sounds ridiculous, does not it? But compared to diving into a white hole or warping space, this method is actually one of the most practical and feasible ways to travel to the future. But this approach has its own problems. Biggest issue is, right now we have absolutely no idea how to safely thaw a frozen person. Because, when you freeze a person to nearly minus 200 degrees Celsius, tiny ice crystals will form inside the body, and these ice crystals are like tiny knives. They tear cells apart and destroy tissue structure. Even if you use the so-called vitrification fluid to prevent freezing, its own chemical toxicity could still damage the cells. In other words, even if you are perfectly frozen, restoration is still an enormous challenge. Freezing yourself is basically like buying an extremely long-term lottery ticket. You are betting on the future of humanity. We really have the ability to solve technical problems that seem like science fiction today. But if you win this lottery, cryonics is actually a true form of one-way time travel. It is not because time around you speeds up, but because you yourself stop. You let the world race ahead. Suppose you are frozen today and wake up in the year 2500. For you, nothing happens in between. You just close your eyes for a moment, but when you open them, you are already in another era. Honestly, that idea sounds pretty exciting. It does not require warping space-time or building some impossible faster-than-light engine. The appeal of cryonics is that it is a very human way of time travel. It is not as flashy as an Alcubierre bubble, nor as out of reach as a white hole, but in a sense, it is even bolder. It is not betting on whether a theory is correct, but rather on science, technology, and a bit of human luck to see if this dream of the future can come true. Among all the future leaping methods we have discussed, cryonics is the only one people are actually trying right now. Its chances of success may not be high, but it is an experiment full of hope. A gamble on whether the future can bring back the past. A pause button with life itself as the stake. Traveling to the future is already hard enough. But what if you are not satisfied with just jumping forward? What if you want to go back instead? Does not that sound completely impossible? But if you are willing to dive into those seemingly unreasonable quirks of physics, you will find this thing. It is actually possible. There is a movie you have probably seen. It is considered one of the most classic time travel moments in film history. It is in Back to the Future. Marty Miffley gets into that modified sports car and hits 88 miles per hour. That number was not just made up. 88 miles. That is the critical point to trigger the flux capacitor. And then what? A dazzling white light. Sparks shoot out from under the wheels. The snap. Marty is instantly thrown out of 1985 and lands in 1955. The whole world loses its familiar neon lights. It turns into a retro world of black and white TVs, vintage cars, and passers-by in wool coats. This is an era you recognize, one that does not belong to you at all. This setup is so fascinating. You do not need a time machine, no higher dimensional theories. You just need to drive. Step on the gas, and you can travel through time. It is like switching to a different highway. You are not going to another city, but to another era. But we all know reality is not that romantic. But do not laugh just yet. Physicists have seriously studied this. Can time be navigated like space? Not just reaching the end, but turning around and going backwards. Speaking of jumping into the future, we have already discussed a bunch of possibilities, from gravitational dilation, relativistic speeds, to freezing time. But going back to the past, that is the real ultimate challenge. And the most ironic thing is, the theory that explains black holes' general relativity actually does offer a few not-so-hopeless loopholes. One of the most enticing ideas is the wormhole. You can think of a wormhole as a hole suddenly squeezed into the fabric of space-time. It is not like a door. It is more like an underground river. The entrance and exit could be separated by billions of light years, or even by two different moments in time. The movie Back to the Future makes time travel look like a teenage adventure game. Timing things, running away, falling in love in a different era, but from start to finish, never explains one thing. How does time get bent? That is what sets it apart from Interstellar. Nolan's setup is not just flashy, it is as close to science as possible. The plot in the second half directly throws a high-concept idea in your face. Time is not a straight line. It can be stretched and distorted by the gravity of a black hole. Do you remember that water planet? Cooper and his team stayed there for a few hours, but when they got back to the ship, their crewmate Romilly had already aged over 20 years. The few hours they spent there were decades on the ship. But what really blew everyone's mind was what happened next. Cooper willingly fell into the black hole, by all laws of physics. He should have been crushed into elementary particles long ago, but he did not die. What he fell into was not darkness, but a hypercube, a higher dimensional constructor space that should not exist. And there, time is not linear. It is not past, present, and future. Instead, every moment is spread out like a giant gap. Every instant is visible. Every second can be touched. He sees every moment in his daughter's childhood room, laid out like a deck of cards spread open, and he, not the one holding the cards, but the one sitting among them. He does not walk through time, he floats in it. What is even more terrifying is this is not a coincidence. The movie sets it up this way. The higher dimensional beings from the future, who are actually humans themselves, build the hypercube and send it back to the past to save himself, who once fell into the black hole. In other words, this closed loop is not a bug, it is a script of fate that was written all along. The initial action leads to the ending, and the ending itself brings about the action, a self-consistent, closed time loop where past and future cause each other. At that moment, Cooper was not saved by the black hole, he was saving time itself. The most amazing part is not that he fell into a black hole, nor that he entered a higher dimensional space. It is that he did not change the past, did not create a paradox. Either everything Cooper did inside the Tesseract had already happened. He did not change history, he simply became a part of it. From beginning to end, he was the one sending the gravitational signals. It was not until he entered the Tesseract that he finally realized that person had always been himself. He did not rewrite the timeline, he completed it. The future and the past are intertwined here, influencing each other, but never breaking causality. There are no split timelines. No parallel universes created. Everything is self-consistent. It sounds shocking, but it actually is not. There is a technical term for this in physics. Closed time-like curve text. We will go into detail about this later, but simply put, time is not a straight line, but a loop that can close in on itself. You walk around it, and your starting and ending points turn out to be the exact same moment. Everything happened exactly as it had to. No more, no less. Here, time is not rewritten, it is fulfilled. That is what makes Cooper's experience in the Tesseract so profound. He did not go back to the past, but he did influence it. It is as if he reached out from the future, touching the past across time without actually stepping into it. It is a kind of time travel that does not break the timeline. It is not time travel, but crossing dimensions. It is about drawing clues from time at a higher level. But here's the question. Is it really possible to send an entire person back to the past? Amazingly, physics says it is possible. How would that work? Wormholes. In theory, a wormhole is a tunnel connecting two distant points in spacetime. You do not have to crawl slowly along the surface of spacetime, but you can go straight through a tunnel under the fabric, like taking a shortcut, jump to a faraway place, or even to another point in time. Imagine. The universe is a huge sheet of paper. You want to go from the top left corner to the bottom right corner. It would take a long time by the usual route, but if you fold the paper, hold the two corners together, then poke a hole through, you can go straight through. That is the idea behind a wormhole. Physicists have an official term for it, the Einstein-Rosen bridge. It is like a bridge connecting different points in space and time, and it is not just space. Time can also be connected. If you can set the parameters correctly, a wormhole can take you not only to distant places, but possibly back to the distant past as well. It is not just about where to go, but when to go. Here's something even wilder. If time flows differently at each end of the wormhole, then it is not just a shortcut through space. It would become a real-time machine. What is going on? Remember time dilation from relativity. If you take one end of a wormhole and attach it to a spaceship, then have it travel close to the speed of light, while the other end stays motionless on Earth, the two ends will start to fall out of sync in time. The flying end, because it is moving so fast, time passes more slowly. On the Earth end, time flows normally. When you dock these two wormhole ports together again, their time clocks will be completely out of sync. If you go in from this side of the Earth, you might come out the other side where you flew in. You could jump straight into the past. If you go the other way, you head into the future. Which direction you choose determines whether you are ahead or behind. You can think of it like an escalator. One side is rushing downward, while the other side slowly rises up. Which side you pick decides whether you travel back to yesterday or forward into tomorrow. In theory, if you travel through a wormhole in the right direction, you really can return to Earth yesterday, but you will quickly realize there is a harsh limitation to time travel via wormholes. You can only go back to the moment the wormhole was created. You can go any earlier. For example, if the wormhole was created in the year 2100, then you can go back to 2050, let alone the age of dinosaurs, because before that, this road had not even been opened yet. It simply had not been opened yet. Because before that, this road had not even been opened yet. That is also why sci-fi movies love to talk about traveling to the future, because the future is a one-way passage, but going back to the past is the real brain teaser. The truly tempting forbidden zone. Wormholes. In theory, it does allow you to go back to your own past. You could even meet your younger self, Sounds too good to be true, of course. There are problems, and they are serious. First, a wormhole has to be held open by exotic matter. Ordinary matter simply can't withstand the gravity at the mouth of a wormhole. Only exotic matter with negative energy density can pull the other way, keep the passage from collapsing. The problem is, we have never actually found anything like that. In theory, it is present in quantum effects. For example, you can detect a tiny bit of negative energy in the Casimir effect, but it is far too little and far too unstable. It is nowhere near enough to build a wormhole frame. The second wormhole is too fragile. Even a bit of radiation, a slight particle flow, or tiny tidal disturbances in space could cause it to collapse instantly. If you are halfway through and the wormhole suddenly closes, it is not that you can get out. You would be torn into quantum fragments by the entire space-time. The third and most controversial, the grandfather paradox. If you really could go back to the past, is it possible for you to do something that completely rewrites your own history? For example, what if you stopped your grandfather so he never had the chance to meet your grandmother? In that case, would you still exist? For example, let us say you receive a text message in the future telling you, do not go on a certain trip. You actually listen and do not go, and end up avoiding a disaster. So where did this information come from? This is what is known as the grandfather paradox and the information paradox. It sounds like time travel would completely break the logic system. But surprisingly, from a purely physical perspective, general relativity does not forbid these things from happening. It even allows for a phenomenon called a closed time-like curve. You go around in a loop and come back to exactly the moment you left. All events are linked together, forming a self-consistent loop without contradictions. It sounds unreasonable, but it is based on mathematics. Physicist Kip Thorne has studied this point in depth. He was the scientific advisor for Interstellar and is a leading expert on wormhole theory. His conclusion is both simple and astonishing. As long as you can create a stable wormhole, in theory, could become a time machine, and it would not violate any laws of physics. Did you catch that? It is not impossible, it is just that we are still a long way from being able to do it. So next time someone says time travel is impossible, you can have a little chuckle, because right now, it is simply not possible. But do not forget, the universe beneath our feet is too vast, too strange, and too restless. It never plays by the rules of our common sense. It is full of loopholes, full of opportunities. History has long taught us one thing. As long as humanity has enough time, things that are completely impossible will eventually be figured out. Maybe that day will really come. We won't just dream about a time machine, but actually get on one. Press the start button. Set off.